Okay, today we want to talk about complex numbers. For the scope of your study, we are not going to go into the history of complex numbers as well as their applications. However, we know that complex numbers got history in such a way that they are related to old mathematicians. But for the sake of this study, we need to understand that we are going to introduce a new number, a new set of numbers that are called imaginary numbers. The reason we use the word imaginary is not because we're trying to imagine them. However, those imaginary numbers, what could they be? There is the idea of square root of a negative number that cannot be found even if you use any type of calculators. You approach any mathematicians, it's impossible to find the square root of -1. And what can we do then in that case? We can just say -1 times 1, which is the same as the square root of -1, because -1 times 1 is -1. In other words, we're saying the square root of a -1 times the square root of 1, and that gives us 1 times the square root of -1, and we are going to represent, because -1 square root of -1 cannot be found, that's a problem, so we are going to replace it by I. And it follows that I square is equal to -1. The reason being is that all imaginary numbers, when you square them, you should end up with a negative number as a result. We can try this by using, let's say, square root of -1 to the square. What does that mean, basically? So it means that you've got -1 to the power of half to the square, because -1 to the power of half is the square root of -1. The 2 and the 2 can cross out, and I'm left with -1. So that means I square, which is the square root of -1, is indeed -1. So all imaginary numbers, when you square them, you should end up with a result that is negative. And also, when we talk about a complex number, let's talk about a complex number. What does that entail? It entails that the number could be z, all right, and that it has what we call an imaginary part as well as a real part. Now z will have two parts, a real part and also an imaginary part. So we could say that z is equal to, let's say, 2 minus 3i. Now that's an example of a complex number. So complex numbers are of the form z is equal to x plus iy, or you could also go and say z is equal to a plus bi or ib. So now let us consider, for example, we've got x squared plus 1 is equal to 0. Now that's an equation. And how many solutions does this equation have in the set of real numbers? Now, for example, if I say that x squared is equal to -1, I'm just trying to solve the equation, which means that this is going to lead to x is equal to plus or minus the square root of -1. And because square root of -1 cannot be found, therefore we have no solutions. There are no solutions, okay, in the set of real numbers. But let us understand now what happens if we say x squared plus 1 is equal to 0, and again we solve it. We got x squared is equal to -1, so that means x is going to be equal to plus or square root of -1, and now we end up with plus or minus I, because we did say that the square root of negative 1 is plus or minus I. Now these are solutions, therefore. Now in this case we have two solutions. Two solutions exist. Okay, two solutions in the set of imaginary numbers. Right, so basically now we can use the laws of surds to extend the use of I to find other imaginary numbers. But before we do that, let's try and understand if we can solve a few questions here. For example, if I tell you to find, okay, the following. Let's say first of all I've got the square root of negative 9. And how do we do this? Basically what we do, so we just split the square root into like 9 times negative 1. So we've got then the square root of 9, which is 3, times the square root of negative 1. So now we're looking at 3 times I. So now that is the square root of negative 9. So that's amazing that we can do something like this. I can try, for example, the square root of negative 5, which basically means minus 1 times 5. And therefore, it's the same thing. Root of negative 1 times a root of 5. We know that this is I, and so we've got then a root of 5i. So now that seems to be our solution to the square root of negative 5. And we can try other examples. Let's try a last one here. So square root of negative 18, and basically we can say 2 times 9 times negative 1. So we're looking at the square root of 2 times 3 times I. So we've got 3 root 2i. That's another example. It's a beautiful one. Now here are a couple of examples. Without using a calculator, we need to find 3i squared plus 3i all squared. For part A of this question, we got 3, which is alone, times I to the square. We know that I is negative 1, plus 3 to the square times I squared. So now we're looking at minus 3, okay, plus we got 9 into minus 1, because I squared is minus 1. So basically now we're looking at negative 12. Now that's our solutions. And also we can try and solve in a similar fashion. Minus 8i, okay, plus minus 4i to the cube. Now if got minus 8i, it is minus 8i. There's nothing else I can do about this. That's a solution already, because we don't have the square root of negative 1 here. It is I, basically. It's there, but it's not in terms of square roots. So what is minus 3 to the cube? Minus 4 to the cube. So that's minus 4 all cube, and then I've got times I to the cube. So if I were to look at this, I've got minus 8i, okay, and this is going to become plus, I can put the bracket here. So this is 4 times 4, 16 times 4, 4 times 4 times 4 is 48. So I've got then negative 48, okay, times, what about the square root, I to the cube. We know that I square is negative 1, so it is I times I. So I've got then negative 1 times I. So that's negative I times negative I. And if I were to take minus 48 times minus I, I'm going to get 48. So that's 48i. And so the minus times the minus becomes the plus. Okay, I'm sorry here, this was supposed to be 64, because 4 times 4 times 4 is basically 64. So that's negative 64. So we're looking at negative 64 times negative I is then 64i. So I've got then 64i minus 8i, and all of that comes down to 56i. So here we are. Sorry about that. It's a bit messy here. Now, suppose if I were to solve an equation that involved complex numbers, let's say 4x squared plus 7 is equal to 0. So let's see how we're going to do this. We're going to proceed as normal. 4x squared plus 7 minus 7 is equal to 0. Take away 7. So we've got then 4x squared is equal to negative 7. Divide both sides by 4. You end up with x squared is equal to negative 7 over 4. So that negative 7 over 4 can be taken as its square root of negative 7 over 4, which is basically the square root of negative 1 times the square root of 7 over 4, and all of that is the square root of negative 1 times the square root separately here of 7 over 4. And of course there's a plus and minus here, we shouldn't forget that, and we've got a plus or minus I, alright, times the square root of 7 divided by the square root of 4, which is then 2. So basically I'm saying I've got a solution as plus or minus the square root of 7 over 2i. So that's my values of x. Okay, extending the same idea to, let's say, a quadratic equation that involves say for example complex roots. I can have, let's say for instance, 5z squared, okay, plus 14z plus 13 is equal to 0. And what if I were to solve this equation? So now we can use the quadratic formula where z is going to be equal to negative b plus or minus the square root of b squared minus 4ac, and all of that divided by 2a. And in our particular example, we know that a is equal to 5, b is equal to 14, and then c is equal to 13. So we're going to take those values and substitute in here. So therefore I've got z as minus 14 plus or minus the square root of b squared, which is then 14 to the square, minus 4 times a times c. And all of that being divided by 2a, that is 2 times 5. So z is going to be equal to minus 14 plus or minus the square root of, now if I were to do the square root of this, I'm going to get 14 to the square. Can you see it here? Alright, it's not very clear. Okay, 14 to the square is this much. Okay, minus 4 times 5 times 13, we end up with negative 64. So negative 64, and all of that divided by 10. Therefore I have z is equal to minus 14 plus or minus the square root of negative 1 times 64, square root of 64, okay, and all of that over 10. So we know that the square root of 64 is 8, and we know that this is I. So then we've got minus 14 plus or minus 8i, and all of that being divided by 10. So if you cross this out, you end up with minus 7 over 5 plus or minus 4 over 5i. So we've got two complex numbers there, and one is plus, one is minus. You can write it as z1 is equal to negative 7 over 5 minus 4 over 5i, and you've got z2 as negative 7 over 5 plus 4 over 5i. So these are the two complex roots for this equation that involves complex numbers actually. So I did talk about the application of surds to complex numbers. We can look at addition of complex numbers. So let us try and see if I can take an example here. Let's say z1 is equal to 2 plus 3i, and we've got z2 as 8 minus I. So if I were to say z1 plus z2, it's very simple. I'm going to take the first complex number, 2 plus 3i, then plus the second complex number, and doing this we end up with 10 plus 2i. So that's my answer. And if I were to subtract, okay, I can use subtraction wherever it's required. So I can say z1 minus z2 over here. So that's basically the same procedure, except now we're going into the minus instead of plus. So we've got then 2 minus 8, which is negative 6, and then 3i minus I is plus I, so that's plus 4i. And what about if I were to do a multiplication of complex numbers? Okay, for multiplication, we can have z1 times z2, and if we were to do this, it's looking more like a quadratic expansion to me, because we've got a set of two factors. Each factor's got a real and an imaginary part. So basically 2 times 8 is 16, okay, and then 2 times minus I is minus 2i, and I have 3i times 8, which is plus 24i, and then minus times plus becomes minus, 3i times I is 3i squared. So we've got 16 minus 2i plus 24i is plus 22i, minus 3 times negative 1. So that means 16 minus means plus the 3 and then plus 22i. So if we do this, we get 19 plus 22i. So here we are. And what about division of complex numbers? That's a little bit more tricky. But once you've learned it, you've mastered it for life. So we're going to look at division of a complex number. Now, when we look at division of a complex number, that's where we introduce the idea of the conjugate of the denominator. Now, you'll understand what I mean by this in just a second. So here we go. We have, let's say, z2 now divided by z1. So we did say that z2 was 8 minus I, divided by z1 is 2 plus 3i. Now, if you perform this on the calculator that's got the complex mode, what you can do, you can just try and check. So 8 minus, and of course you won't have this option in the exams for CIE, for Cambridge, and then plus 3i, so this is 3i, and you're supposed to get 1 minus 2i. So let us see if we can reach and get this answer, 1 minus 2i. That's what our calculator is giving us. This is our denominator. The denominator here is z1, so that's our denominator. It is z1. And z1, if we want to find its conjugate, if this is 2 plus 3i, the conjugate would be then 2 minus 3i. So what we do then is we use rationalization from surds. So we multiply the numerator and the denominator by the conjugate of the denominator of this complex number, so 2 minus 3i. And let's perform our multiplication here. I've got the numerator. So 8 times 2 is 16, 8 times minus 3 is minus 24i, minus I times 2 is minus 2i, and I've got minus I times minus 3i is plus, so I've got then plus 3i squared. So over here divided by, now for the conjugate of the denominator, here I've got these two are difference of two squares from quadratic expansion. We know that a square minus b square is always a minus b times a plus b. So what we have is a plus b, a minus b, so which is equivalent to a square minus b square. So I can say then 2 to the square minus the 3i to the square. So let's see. 16 minus 24 minus 2 is minus 26i, and then plus the 3 means 3 times minus 1, because I squared is minus 1. That we've learned from the beginning. This turns out to be 4 minus here. I've got 3 to the square, which is 9, times I square. So I'm looking at 16 minus 3 is 13, then minus the 26i. And all of that divided by 4 minus 9, because 9 times I square is negative 9. And so I've got 13 minus 26i, and all of that being divided by 4 minus means plus, so that means 4 plus 9, which is then 13. And basically I'm saying then that this is going to be 13 divided by 13 is 1, okay, and then minus 26 over 13 is 2, and you got the I there. So this is your Z2 over Z1. Right, so this is how we perform a division that involves complex numbers with imaginary as well as real part. Okay, now I would like to solve an equation that involves complex numbers again. So find the value of x and the value of y in the following. And I've got, this is our real part, and that's our imaginary part. And there we got here real, and here imaginary. So the real part and the imaginary part, okay, can be equated to each other. So I mean real to real, imaginary to imaginary. So I can say therefore x plus 2y, the real part here, is equal to the real part on the right hand side, which is 1. And then for the imaginary part, I've got 3x minus y is equal to the imaginary part on the right hand side is 10. So I've got a pair of simultaneous equations. Isn't that amazing? Because it becomes very easy to solve a pair of simultaneous equations, which could be solved by elimination method. So this is, this is y, okay, 3x minus y. Okay. So now we can multiply this by 1 and multiply this by 2 and try to cancel y. So I've got then x plus 2y, the usual way of solving your simultaneous equation. Then I've got 6x minus 2y is equal to 20. So now if we would like to cancel y, we simply need to add, and these two is going to cancel out, and I'm left with 7x is equal to 21, meaning that x is 21 over 7, and therefore I've got x is equal to 3. And we can pick any of those equations. Let's take the first one, for example. So let's take x plus 2y is equal to 1. Now we know that x is 3, so we've got then 3 plus 2 times y is equal to 1. So 2y is equal to 1. You take this, the 3 on the other side becomes minus. So I've got 2y is equal to negative 2, and therefore y is equal to negative 2 divided by 2, which is then negative 1. So we've got x is 3 and y as negative 1. And here we are. That's how we solve such type of an equation where it leads to a simultaneous equation. This is very important because it's going to be used, we're going to use this in finding square root of a complex number later on in this tutorial. You take care. Bye.